Welcome to Learning Outcome 3, all about correlation, the idea of whether two things move together and how strongly. It's one of the most useful and, honestly, most misunderstood ideas in statistics, so let's get it right. We start with bivariate data, which just means we record two variables for each item. Think revision hours and exam mark for each student. Correlation describes whether those two variables are related and how strongly. We're looking for a pattern. As one goes up, does the other tend to move too? But here's the crucial caveat we'll keep returning to. Correlation, on its own, never proves that one variable causes the other. Correlation comes in three broad types. Positive correlation is where, as one variable rises, the other tends to rise too. Hours studied and marks earned, for instance. Negative correlation is the opposite. As one goes up, the other tends to fall, like the price of a product and the quantity people demand. And no correlation means there's simply no clear relationship. The values wander about with no trend at all. The scatter diagram is our main picture for this. We plot one variable against the other, one dot per item, and the shape tells the story. Points that rise from left to right show positive correlation. Points that fall from left to right show negative. A shapeless cloud with no direction means little or no correlation. And there's a second dimension too. Strength. Points hugging a line are strongly correlated. Points widely scattered only weakly so. Direction and strength both matter. A few practical tips for drawing one well. Put the explanatory variable, the one you think does the influencing, on the horizontal axis and the response variable on the vertical. Choose a sensible scale so the points spread out and fill the graph, rather than bunching in a corner. Plot each pair as a single point, and crucially, don't join the dots. Then step back and look at the overall shape before you draw any line. Is the trend roughly a straight line or something curved? Once you can see a linear trend, you draw a line of best fit, a single straight line passing as close as possible to all the points, with roughly equal numbers above and below it. A reliable check is that it should pass through the mean point, the point whose coordinates are x bar and y bar. That line summarizes the whole trend and lets us estimate one variable from the other. Software can find the exact least squares line, but at this level, a well-judged line by hand is perfectly acceptable. Let's see it on real figures. We plot 10 students' revision hours against their test marks, and the points climb clearly from left to right, a strong positive correlation. Our line of best fit passes neatly through the mean point, and its equation turns out to be y is approximately 5.3 x plus 25. That little equation captures the trend in a nutshell, and once we've got it, we can read estimates straight off the line. Let's use that equation. Y equals 5.3 x plus 25. How would a student who revises for 8 hours do? Pop in 8, 5.3 times 8 is 42.4, plus 25 gives 67.4, so about 67%. Now the other way, what revision would you need for a target of 60? Set 60 equal to 5.3 x plus 25. So 5.3x is 35, and x is 35 divided by 5.3, roughly 6.6 hours. Both of those sit comfortably inside the range of our data, so this is interpolation, which is reasonably safe. Just remember, estimates are guides, not guarantees. That word interpolation is worth dwelling on. Interpolation means estimating within the range of the data you actually collected, and it's generally reliable. Extrapolation means estimating beyond that range, and it's often anything but reliable, because the pattern you saw may simply not continue. Predicting a mark for 40 revision hours from data that only stretch to 11 hours is a real gamble. So always be clear whether an estimate is interpolation or a riskier extrapolation. Here's a vivid example. A baby's weight climbs steadily over its first few months, giving a lovely, strong, positive line. Within that first year, the line predicts weight nicely. That's interpolation. But extend the very same line out to age 20, and it would forecast a weight of hundreds of kilograms, which is obviously absurd. The linear trend just doesn't carry on. Growth slows and eventually stops. It's a perfect illustration of why you should only trust a line across the range of data used to build it. Now the big one, correlation is not causation. A strong correlation does not prove that one variable causes the other. There may be a lurking third factor, a confounding variable, that's actually driving both. Or the link could be pure coincidence, which happens surprisingly often in small samples. To genuinely claim that one thing causes another, you need controlled evidence, not just a promising-looking correlation. The classic example makes the point beautifully. Across the summer, ice cream sales and cases of sunburn both climb together, giving a strong positive correlation. But it would be daft to conclude that eating ice cream causes sunburn. The real culprit is a third variable, hot, sunny weather, pushing both up at once. That's a confounding variable creating what we call a spurious correlation. The pattern in the data is real, but the causal story is false. Always ask what else could explain a relationship before you claim cause and effect. So far, we've eyeballed scatter graphs, but we can put an actual number on the relationship, a correlation coefficient. It always lies between -1 and +1. +1 is a perfect positive relationship, -1 a perfect negative one, and 0 means no linear relationship at all. Values near either extreme signal a strong relationship. Values near 0 a weak one. The particular coefficient we'll use is Spearman's rank correlation coefficient, which is based on ranking the data. Spearman's coefficient, written R sub S, compares the rank order of the two variables rather than their raw values. The recipe has 3 steps. First, rank each variable separately, say from highest to lowest, being consistent. Second, for each item find D, the difference between its two ranks, then square it to get D squared. Third, apply the formula R sub S equals 1 minus, in brackets, 6 times the sum of D squared, divided by N times, in brackets, N squared minus 1, where N is the number of pairs. Let's organize the working in a table for 6 students. We list each one's revision hours and mark, then rank the hours and rank the marks. Student A has the most hours and the top mark, so both rank 1. Student B is second on both, and so on down to student F. When the ranks line up this closely, the differences D are all small, in this case mostly 0, and that already points us towards a strong positive correlation before we've even finished the sum. Let's complete it. For each of the 6 students we work out D, the difference in ranks, and square it, then total those up. The sum of D squared comes to 2. With N equal to 6, we need N times, in brackets, N squared minus 1, which is 6 times 35, giving 210. So R sub S is 1 minus 6 times 2. Divided by 210, that's 1 minus 12 over 210, which comes out at 0.94. An R sub S of 0.94 is very close to +1, a strong positive correlation, just as the scatter suggested. So what does 0.94 actually tell us? It confirms what the scatter graph hinted. More revision goes hand in hand with higher marks. As a rough guide, 0.8 to 1.0 counts as strong, 0.5 to 0.8 as moderate, and below 0.5 as weak, whether positive or negative. A coefficient near zero means no monotonic relationship, though not necessarily no relationship whatsoever. And always report the sign as well as the size. Minus 0.9 is every bit as strong as plus 0.9, just pulling in the opposite direction. Spearman's isn't the only game in town. Pearson's product moment correlation coefficient, usually just called R, measures linear correlation using the actual values rather than ranks. Like Spearman's, it runs from -1 to +1 with the same reading of strength and direction. Spearman's is easier to do by hand and copes well with ranked or steadily increasing data, whereas Pearson's is the one you'd prefer when the data is roughly linear and measured on a proper numerical scale. Let's bring it into business. A shop compares its weekly advertising spend with its sales revenue over 8 weeks and finds an R sub S of 0.82. That's a strong positive correlation. Higher advertising tends to go with higher sales, and the manager could use a line of best fit to estimate sales for a planned budget. But correlation isn't proof. Seasonality or a price change might also be lifting sales. The sensible next step is to test the link directly, perhaps by trialing different spends and measuring the effect. A few honest limitations to bear in mind. A correlation coefficient only detects a consistent, one-directional trend, so it can miss a genuine but curved relationship. Outliers can distort the result, Pearson's R especially. A small sample can throw up a high coefficient purely by luck. And as we keep saying, correlation never establishes cause and effect on its own. The good habit is to report the coefficient alongside the scatter graph and the sample size, and never to claim causation from correlation alone. Let's draw learning outcome 3 together. Correlation describes the relationship between two variables, and scatter diagrams reveal its direction and strength. A line of best fit passes through the mean point, X bar and Y bar, and lets us estimate one variable from another. Interpolation within the data is reliable, but extrapolation beyond it can give absurd results. Correlation is not causation. A confounding variable can manufacture a spurious link. And Spearman's rank coefficient gives us a single number from -1 to +1 that captures the strength and direction of the relationship. That's correlation covered, from scatter graphs right through to a calculated coefficient. You should now be able to spot a trend, draw and use a line of best fit, and just as importantly, resist the temptation to leap from correlation to cause. To go deeper, Roundtree's Statistics Without Tears is a gentle read, and Crawshaw and Chambers gives fuller worked examples of Spearman's and Pearson's. The Significance magazine from the Royal Statistical Society has some genuinely entertaining pieces on spurious correlations, and Corbett Maths will walk you through the rank calculation again if you'd like. Do try one by hand. It's the best way to make it stick.